Hello and welcome to the second lecture on software engineering for students. In this section we will be looking at the tasks which have to be conducted in order to complete a software project development. Now, as part of this story we have to clarify the nature of the tasks at hand, and if you've ever conducted a development of any software project, you will know that there are two main things that take up your time, and that is the gathering of all the requirements for the users as well as the testing processes. Now, within this section we're going to look at the development of larger software projects. So there are many more tasks involved in these, and these can involve a feasibility study, obviously the gathering of all the requirements for the users, and many aspects of the design as well. And obviously we do have the coding, the integration, and the testing in that as well. We will also be looking at the production and the documentation of the final project, as well as the maintenance and the project management aspects. So let's begin by quickly talking about the process models. Now, at the end of this chapter, I will go into much more depth as to the process models which can be used. However, generally a process model will combine all of the tasks into something which is a bit more methodical in its manner. And it may seem quite obvious that things could be carried out in a certain order, but sometimes you have instances where you can not conduct the testing at the end, and instead you will do it after every module is built in the system. Alternatively, there is the waterfall method, which allows you to test at the end. But as I say, we will go into this at the end of this lecture. Worthwhile to be conducted or not. And this can be done in many ways, but the most common method is to do a very detailed analysis in order to understand the costs and the risks involved in the system. Now, as previously mentioned in the first part of this session, the costs can be quite hard to predict, and as such this makes the feasibility study a little bit more difficult in doing. However, the risks are quite easy to understand, and therefore we can do somewhat of an analysis on this. So before actually beginning the project, the one crucial question which is asked is that, is this project technically feasible? That is the technology currently in existence in order to actually build this project? We know, obviously, as an example, that in order to predict the lottery, well, we can't do anything, can we? Because there is nothing that exists to do that. But, for example, we can build a system to recognize voice commands at the moment, and this is speculation as to how good these are, but you know, the technology currently exists in order for people to do that. The biggest thing which is conducted is the cost-benefit analysis. Now, in engineering, there's been a long tradition of assessing the available technology and obviously having a look at the cost-benefit analysis. Now, money provides the ready-made metrics for measuring value, and this kind of investigation is called an investment appraisal, or a cost-benefit analysis. The organization expects a return on the investment that they make, and this is calculated by two methods. Firstly, the cost of actually providing and implementing the system, and secondly, the money saved or created by using the system, which is therefore the benefit. If the benefit is greater than the cost, then the system is worthwhile. Otherwise, it is not. If there are some other ways of accomplishing the same task, which may be which may be done manually, it is then a good idea to compare the two together. Whichever technique has the smaller cost is the one to select, obviously, because you need to factor in the cost to benefit. As we said, it has to be of benefit to the client, and you as the software developer need to ensure that you are not going to charge too much where there isn't enough benefit. Now, many evaluation criteria are common in all computer systems, and indeed to all products that are designed for the same purpose of being useful. Cars, televisions, buildings, they all have to be reliable, robust, and easy to maintain and upgrade when the time comes. The central consideration is always going to be the cost of construction, which obviously we can associate with some of these. So, for example, the cost to buy the equipment, hardware in our instance. So how much is it going to cost to implement the servers and networking and so on and so forth? How much is it going to cost to actually then build the software which is going to go on top of this? The cost of training. Now, this can be kind of a double-edged sword, because you may have to train extra staff to actually do the project in the first place, and then once it's done, you need to train people in the client's organization to actually use the software. So this, again, brings in a lot of cost. The cost of lost working due to the switchover. So you may have a project which is being taken over, by yourself, from another organization or internally, and this can cause a couple of issues as well, and obviously increase the cost. Then we have some more serious matters, such as the cost to actually maintain the system. So, as we have previously mentioned, there are a couple of maintenance issues which we must look at, and I will go into detail in those in a later section of this subject. The cost to repair equipment if anything fails. Obviously, we know that nothing is 100% reliable, and servers always crash, always have problems. So what's going to be the cost, obviously, if anything happens to our critical infrastructure? And finally, the cost to upgrade, because our servers and our software are not going to last forever, and therefore we need to look at this in a little bit more detail. The upgrade cost is part of the cost of the future system, essentially, and not strictly part of the current costing, but it's worth bearing in mind, obviously, at the time of the evaluation. While all these costs should be estimated in advance, it is in practice it's quite difficult to estimate at the beginning all these costs. So sometimes it is split out over time. Aside from this, of course, there are other criteria that exist, and it's quite easy to be drawn into judging everything on the basis of costs. The first of these is actually open source programming. Now, a lot of people actually do develop for fun, including myself, and often we do publish these pieces of software just because it's a helpful tool and people can take advantage of that. Now, some people may be seduced by technology and take the view that computer systems are obviously better than manual systems, and therefore they may build something to help themselves as opposed to for commercial use. Some systems are, of course, socially useful, and perhaps outside the scope of the costing-based approach. Now, how can we meaningfully assess the value of system which allows a person to book a medical appointment, or a system that provides arrival times for the bus stops. So the next section looks at the requirements gathering. Now, logically, the first step of any software development project is to establish precisely what the users need and what they want from the system. The dominant part of this stage is to have an open line of communication between the users and the software development team. When the engineers are dealing with the requirements, they are normally referred to as the analysts. And this term is what we shall be using in this section. As far as the users are concerned, there are sometimes obviously known as clients or customers. We will use user. Now, the task of analyzing and actually defining the requirements of the users is not a brand new or a peculiar idea to software engineering, and for generations it's been carried out as an activity. Let's have the example of, on a dry track, the locomotive must be able to start the train of up to 100 tons on an incline of up to 30% with an acceleration of at least 30 kilometers per hour. Now, this statement serves to emphasize the requirements, and it tells us what the user is after. It says nothing about how it should be built, and thus it does not state whether it is diesel, coal, or any other form of power. It also says nothing about the shape or the wheel arrangement. One of the greatest controversies is whether it is desirable or even possible to specify what a system should do without considering how it will be built. Now, this is the relationship between specification and implementations. We will look at both sides of the arguments very quickly here. Now, on the one hand, there are several reasons why the requirement specification should avoid implementation issues. The prime reason is that the user cannot reasonably be expected to understand the technical issues of implementation, and therefore, it can be expected to agree with elements of the specification. To emphasize the point, how many users of a word processor really understand how the software works? A second reason for minimizing implementation considerations is to avoid basically unduly constraining the implementation. It's best for the developer to have free rein over whatever tools and techniques he chooses, just as long, obviously, as the requirements are met. The other side of this is that some people argue that it's impossible to separate the specification and implementation considerations. Indeed, in several major approaches to specifications, they are intermixed. In such a method, the first task is to understand and to document the workings of existing systems. So this might be a manual or a computer-based system, or however you want to do it. And this investigation will serve as the prelude to the development of a computer system. Thus, the implementation of one system acts as a major ingredient in the specification for the new system. For example, suppose we wish to develop a computer system or a library, and it currently has no computers. One approach would be to investigate and document all the current manual procedures. The next step would then be to actually decide which areas of activity would be computerized. Finally, the specification of the new system is derived from the design, i.e. the implementation, of the old system. This approach to development seems very appealing and logical. However, it does mean that the implementation and specification are intertwined. There are several additional powerful reasons why the analyst has to think about implementation during the specification. Firstly, they must check the requirement is technically possible, as we were discussing earlier about the technical feasibility. And secondly, it is vital to consider implementation, in order to estimate the cost and the delivery date of the software. Now, in order to estimate the figures of performance and cost, it will almost certainly be necessary to carry out some outline development, at least, as far as architectural design is concerned. So, next we will be looking at the qualities of a specification. Now, we have seen that, ideally a specification should confine itself to what it is. Now we must look at the qualities of a specification. So we've seen that ideally a specification should confine itself to what is actually required. So in this we're now going to present what a good specification is going to exhibit. Now, firstly, it should be implementation free. What is needed, not how it is achieved. Secondly, it has to be complete. There is nothing actually missing from the specification. Thirdly, it has to be consistent. No individual requirement contradicts any other requirement. It must be completely unambiguous. Each requirement has to have a single interpretation. It also has to be concise. It should only be said once and without any duplication. It must be minimal. There are no unnecessary ingredients to the requirement specification. It also has to be understandable by both the clients and the developers. It also has to be achievable, so the requirements must be technically feasible. And lastly, it has to be testable. It must be demonstrated that all the requirements have been met. Now, a requirement specification should also be able to provide clear guidance as to how to check the system will meet the user requirements. In the specification for the locomotive that was given above, there is plenty of quantitative information that will allow you to be quite objective about it, to be clear, and all the communications must be understandable for a later use. The skills involved on the part of the analysts are not the usual technical skills that are associated with the developing of any software. It is beyond the scope of these lectures to actually explore the issues of human interaction, and we shall largely concentrate on the format of the specification. We will, however, touch on these few issues, and that is that the analysts and the users both have to have listening, thinking, and writing skills. Pretty obvious. Elicitation involves listening to the user requirements, asking questions in order to assist the users in clarifying the goals and the constraints of the actual requirements. The requirement analysis is the stage where the software engineer simply thinks. He or she transforms the user's view of the whole application into an organized representation of the system as seen by the analyst. The requirements, actual definitions, is the writing of the clear statement, and if you're an analyst, you must have some sort of good communication writing skills in order to get across your point effectively. As in any complex process of any communication or negotiation, these three activities mentioned are absolutely important. So, the requirement specification. Now, the end product of the requirement elicitation is basically a specification, which can be designed to obviously meet all the requirements of the users. It is a vital piece of documentation that is crucial to the success of any software development project. If we cannot precisely state what the system should do, then how can we develop the software with any confidence? And how can we hope to check that the end product is going to meet the actual user's needs? A specification is obviously our point of reference against all the subsequent development. Three important factors must be considered. Number one, the level of detail that is included. Secondly, to whom the document is addressed. And thirdly, the notations which are used. Now, the first factor is about the need to restrict the specification as much as possible to specify what the system should do rather than how it should do it. As we have seen, the specification should ideally be of the view of the users rather than anything about how the system is going to be implemented. Second factor arises because the specification has to be understood by two different sets of people, the users and the developers. The people in these two sets have very different backgrounds, expertise, and jargon. They share common aim, clearly, to actually build the software itself. The users will have a preference for something that is, non-technical and expressed in a very natural language. Unfortunately, while the natural language is excellent for poetry and love letters and so on and so forth, it's a poor vehicle for actually achieving the consistency of a specification. On the other hand, analysts, being of a technical orientation, will probably want to use precise language in order to specify the requirements. This brings us to the question of the notation. Several notations are available for the writing of the specification: informal writing, formal writing, semi-formal writing. And obviously it is down to the user of the system to actually tell the analyst how to do things. And it is then down to the analyst to come up with the relevant specifications. You essentially have partitions in the specification. So in the specification, all the corresponding elements are called functional and data requirements. One of the major debates in computing at the moment is which of these are the main elements, the functional or the data requirements. Some approaches to the development, as an example, object-oriented approaches, are holistic, and they are treating the function and the data with equal importance. However, a concern here with the specification is with itself the specification, not the development approach. However, the actual format of the specification tends to reflect on the approach which is employed. So a checklist of the contents. Firstly, we need to include the functional requirements. The functional requirements are the real essence of the specification. They state what the application will actually be doing. The data requirements have three components. Number one, the user's data that is inputted or is outputted from the system through the screen or the keyboard or the mouse. Number two, the data that is stored within the system, usually on a disk. For example, information about the books that are held in a public library. And thirdly, information that is passed to or from another computer, as an example, a server. Next, we have the performance requirements. There are several Next, we have the performance requirements. Now, there are several measures to the performance, some of which are qualitative, some of which are quantitative. And some of these can be found as a part of testing. Now, examples of these include the cost, the delivery date, the response times, the data volumes, the loading levels of the system, the reliability requirements, and the security requirements. The constraints, these are basically influences on implementation of a system. Examples of these can be that the system is going to be written in Java. Now, constraints are going to deal with the computer hardware that is going to be used, the amount of RAM which is available, the amount of space on the backup storage, and the interoperability constraints. Now, these constraints often address implementation issues, and therefore should be included with caution. For example, there might be unnecessary constraints within the specification document. And finally, we have the guidelines. Now, the guidelines will provide a very useful direction for the implementation in any situation where there may be many implementation strategies being used. For example, the response times of the system to mouse clicks should be minimized. Many specifications will mix up areas identified above, so that, for example, the design guidelines are sometimes confused with the functional requirements of the system. This obviously isn't the ideal situation. So, why are we doing the requirement gathering process? So, as outlined previously, we need to understand what the users will actually be using the system for and how they will be using it. Now, one widely used approach to documenting the requirements is use cases. These are textual-based descriptions which are basically augmented by the UML case diagrams. Use cases take the point of view that the users of the system are sitting there and explaining all the relevant functions. A user who is carrying out a particular role is called an actor. A use case is the task that an actor is going to have to carry out on the system. For example, in the ATM system, one of the things that the user has to be able to do is obviously take out cash. This is a use case. So you will see that there are some different types of use cases which will come up quite commonly throughout any system. So use case diagrams allow us to document the use cases in a UML case diagram. As can be seen on the screen at the moment, there is a very simple use case diagram illustrated. That the user is going to be communicating with. So it's of paramount importance that this is done well. So the interface is essentially the packaging for the software. The user, he doesn't care how it works, but instead they care as to what it does and how to use it. If it is easy to learn, simple to use, and straightforward, the user is going to be encouraged to obviously make use of it. If not, they won't. The user interface is often the yardstick by which a system is judged. Interfaces can be hard to learn, difficult to use, unforgiving, and sometimes totally confusing. At worst, it will cause the software to be discarded and irrespective of its functionalities. There are often challenges to the interface design. Now, user interface design offers the software engineer some principles to guide interface design, some guidelines for interfaces, a process for developing an interface, and obviously based on prototypes, and obviously the methods for evaluating the interfaces that have been created. Now, styles of human-computer interface is quite a complex subject. The manner in which a user will tell a computer what they want to do has changed dramatically over the last couple of decades. Broadly, there have been three types of interfaces: the command line, the menu, and the graphical user interface. So in the early days, it was all command line, and we still do use command line nowadays in certain servers, but this has now gone away and has been replaced with the graphical user interface. So there are many different perspectives on a user interface design. In designing a user interface, it is as well to realize that there are several potential viewpoints. The perspectives are the end user, who will actually be using the system, the different end users with varying personalities. There'll be people who don't really know what they're doing with the software, and there'll be people who are very experienced. So the software developer has to take all of these into account. Now, most people do not apply for any formal reasoning when confronted with a problem, such as understanding what a computer is displaying. Rather, they apply a set of guidelines, rules, and strategies which are based on their understanding of any other problem that they have faced. And these are called heuristics. These heuristics tend to be very domain specific. An identical problem encountered in an entirely different area may be involved in this problem solving scenario. The problem is that different people often have very different perspectives on the user interfaces. They also have very different skills, culture, and personalities. Each person obviously comes with their own set of these. So the skill level of the end user has a big impact on the ability to extract any meaningful information from the user interface and to respond efficiently to tasks that are demanded by the interactions. For example, an engineer who uses a computer-based diagnostic system is able to find faults in cars and understand the problem domain, and can interact effectively through an interface that has been specifically designed to accommodate his background. This same interface might confuse a doctor, even though the doctor has experience of using a computer system for certain diagnostics. So the design principles and guidelines. Now, the design principles are high-level principles that can guide the design of the user interface. Three overall principles are used, and these are the learnability aspect. So how easily can a person who has never used it before learn the system? How flexible is the interface in its style and its its variety, and how much feedback can it offer, and obviously confirm all the aspects that are going on. Now, each of these can be broken down into a few more aspects. However, this is not within the scope of this lecture, so we shan't go too much deeper into this. Now, the actual interface design itself can be broken down into as is shown on the screen. The human and computer-oriented tasks can obviously be done through the interface using the principles outlined on the screen, where we have to first construct the prototype. This will then be checked with the user to ensure that it is, okay for their use. If it's not, then obviously the developers are able to go back and change things to come back and then check again. And this is often, repeated many times in order to get the correct interface design. As mentioned previously, the three principles must be incorporated into the interface itself. And this concludes the first half of Lecture 2 on the tasks of software engineering. In Part 2 of this lecture, we're going to look at modularity, structured programming, functional decomposition, data flow diagrams, the data structured design, and the design patterns, as well as refactoring.